Okay, welcome to the review for the third midterm. The third midterm is again 8 to 8:30 Monday, Wednesday, Fridays, this time in week 13. It's online in Canvas as usual. Again, if there are real problems in submitting, then just screen capture, take a photo and send it immediately to me or to Shinshin and we'll take care of it. Material covered in this third part of the class is what we did in week 8 on conservation of energy, what we did in week 9 in dimensional analysis, and then in weeks 10 and 11 in pipe flow. And it omits the material talked about in the last part of week 11, which is pipe networks, multiple pipes. The 3 individual questions are on Monday, energy equation and pipe flow. There's always a question on dimensional analysis, and that's the middle Wednesday test, and then pipe flow on the Friday. So to go through each of these materials, just in quick review, we talked about the energy equation in week 8. We talked about the idea that there is an energy grade line that we can define, and a hydraulic grade line that we can define over systems, and that these represent the behaviors in terms of Bernoulli, the elevation head, the pressure head, and the velocity head, all added up at the upstream and the downstream location. We know that when we use the energy equation, we have to write it between upstream and downstream and follow that convention. And if we do, then if we have a pump head that's in the system, then a positive pump head is working as a pump, which adds energy or head to the system, and a negative pump head subtracts from the system and represents energy removed from the system, which is basically a turbine. We also, for real systems with energy losses, we have head losses, which are due to frictional losses along the pipe as it flows from upstream to downstream. And we can incorporate that into the one-dimensional energy equation, which is just the Bernoulli equation upstream, the Bernoulli equation downstream, with a pump head, which is positive if it's energy into the system, which is negative if it's energy out of the system, and with head losses, which are always positive, and net losses of energy to the system. You have to be careful that if you're writing behavior from upstream to downstream, that if in a large tank, you'll have zero velocities in the tanks, but the velocity that gets factored into the head loss equation is the velocity within the pipe. And the velocity in the pipe is not going to be zero, even if the velocities in the upstream and downstream tanks are. And so you have to incorporate that into this head loss equation here. There are 2 forms of losses which contribute to this H sub L loss. There are minor losses, which are losses in bends and fittings, which are a function of some loss coefficient. Typically, this is between 0 to 1. It has no dimensions because the dimensions of head loss are the same as velocity head. So this is dimensionless, but it typically varies between 0 and 1. It isn't limited to less than 1, but typically it is. And the major losses, which are small incrementally, but are integrated over the long length of the pipe and the diameter of the pipe, which again are defined in terms of the velocity head, length to diameter ratio of the specific pipe, and some kind of friction factor, which is a function of whether we're laminar or turbulent. In terms of the pump head magnitudes, we can define that, again, positive or negative for pumping or a turbine in terms of the power, uppercase W dot, which is in watts, and the mass flow rate and gravity, or again, the power as a function of volume flow rate and density, which together, of course, is the mass flow rate and gravity. And the mass flow rate is just the average velocity in the pipe multiplied by the cross-sectional area. And so that's relatively straightforward to determine. If we look at pipe flow, the essence of pipe flow is indeed this relationship here, where the friction factor defines the loss within the system. We've talked about how the friction factor is a function of whether it's either laminar flow less than a Reynolds number of about 2000, or turbulent flow, where it's greater than that number. And the characteristics of the friction factor are different in those two regimes. In the laminar regime, the friction factor is an inverse function or reciprocal function of Reynolds number. And so if we want to be able to manipulate that, we can write this out in terms of 64 divided by the Reynolds number, which is a density, a velocity, a characteristic dimension divided by a viscosity. And so if we want to be able to define a head loss in terms of this friction factor, we can write the head loss in terms of the friction factor, length over diameter, and v squared over 2g. And we can incorporate this relationship into this value. And of course, one of the values of the velocity in this term will cancel out with this velocity, and you'll end up a linear function of velocity, and you can solve for velocity. So in the turbulent regime, the laminar regime, we can define it in terms of Reynolds number, and it knocks one of the velocities out in this term here, and we solve for head loss as a function of a velocity. Conversely, if we're in the turbulent regime, then the friction factor is a constant with Reynolds number. It doesn't vary with Reynolds number. And therefore, this value here is a constant. And so if we know what the value of the head loss is, we can square root this term to be able to determine what the value of the velocity is. So there's two fundamental different ways in which to solve for the velocity if we're laminar flow or turbulent flow. And that is just realizing that this friction factor is a function of velocity for laminar flow, and it's not a function of velocity for turbulent flow. And therefore, the form of solving this equation changes as a function of that. If you need to use Moody charts, we can define a number of types of solutions for the problems. So if you're given a velocity in the pipe, that makes life easy because it defines an absolute Reynolds number. A Reynolds number defines an absolute magnitude of the friction factor, either within the laminar regime. If you know what the Reynolds number is, you know immediately what this friction factor is. In the transitional regime, if you know the Reynolds number, you also know what the friction factor is for a smooth pipe. And if you're in a turbulent regime, so long as you know the relative roughness of the pipe, then the friction factor is independent of the Reynolds number, but is still recoverable in the same way. So for all of those cases, if we know the Reynolds number, if a velocity is prescribed, then we can solve directly for friction factor. For type 2 equations, then we don't necessarily know the velocity, but we have to solve for the velocity. So in those conditions, we typically have to make a guess of a velocity, use that velocity to calculate a Reynolds number, check the Reynolds number to get the friction factor, calculate what the velocity is from the friction factor, and then recheck the value of Reynolds number to be able to make sure that we're relatively close to it. And so we have to iterate towards a solution in that particular case. So that's the energy equation and pipe flow, which is utilizing energy losses. The final feature, which we talked about in week 9, is so-called dimensional analysis. We can define a method to be able to define non-dimensional coefficients. It's called the Buckingham pi theory. And all we need to do is define the number of variables in our problem. We solved a fluid flow in a pipe problem, which had slightly different variables. I guess it had delta P is equal to these terms. But if we can define all the variables that describe our problem and count how many there are, diameter, density, velocity, length, and viscosity, a total of 5 variables define our system. If in those variables we have mass, length, and time all represented, then we know the number of units we have represented in our system. In this, we have mass over length, and we have length over time, so we have all mass length and time represented. So 5 minus 3 gives us the number of pi groups that we have that define our system. And so for those pi groups, if we define some repeating variables, in this case, if we define diameter, density, and velocity as the repeating variables, as in these, then we can take each of the remaining parameters in turn and apply those to the different pi groups. And so the first one is we'll use length. This will be the complete group. We have an exponent A, B, and C to be able to solve for. We set this so that the units of mass, length, and time together sum to 0, because the exponents here have to have no dimensions. And as a result of that, we can get values of A, B, and C for these variables. We can substitute it back into this expression, and we'll end up with a non-dimensional variable. And this would be typically either Euler number or Reynolds number. If we do the second dimensionless group, then we'd use the next parameter. We'd tack that on here. Again, we'd use diameter, density, and velocity raised to these powers. We'd solve for new values of these coefficients, and this would define our second non-dimensional variable in terms of what these exponents are applied onto these units. With both pi 1 and pi 2 determined, and typically this pi 1 might be Reynolds number and pi 2 might be an Euler number. It certainly was in the example we looked at. Then it says that if we look at having the flow similarity in our system conditioned by the Reynolds number, then because only two groups define the behavior, there must be some unique curve between them. If we have a third pi group defining behavior, then we'd end up with a curve for different values of pi 3 is equal to 1, pi 3 is equal to 10, etc. But if we only have one of these, only have two pi groups, then a unique value of Reynolds number gives a unique value of Euler number. And so you can use that to scale between experiments and prototypes. And so the example we also went through in class was that we looked for three different conditions. We looked for geometric similitude, and that is the ratio of all lengths in the model to the prototype are constant. So the model is a scale model in every dimension of the prototype. We look at kinematic similitude, which means the Reynolds number in the model and the prototype are the same. And so the flow regime around the structure is going to be identical. If we have vortices releasing off the model because the Reynolds number in the model is equal to, say, 4,000, then we want to make sure that in our prototype we have exactly the same geometry of flow, and so that Reynolds number would have to be 4,000. And so we could choose what the velocity either in the model or the prototype would be to have that similitude in the Reynolds numbers. And then if we want to calculate what the forces or pressures are between the model and the prototype, then we make sure that the Euler numbers between those systems match as well. In other words, we look at dynamic similitude. So if we measure the forces on a structure in a wind tunnel, which is a model, then we can convert those forces on the model to the forces on the prototype merely by making sure that the Euler numbers are the same. And so this intercept would be the same between model and prototype. And therefore, from the Euler number being the same for model and prototype, we can calculate what either the pressures or the forces on the model would be. And the explanation of that is just by the idea that if two pi groups define our system, then it means that there's a relationship that's a unique relationship that links these, so that if you have a given value of the pi 1 variable, that represents a given value of the pi 2 variable. And typically Reynolds number might be the pi 1 and Euler number might be the pi 2. And if we have more than those two variables, say pi 3 for instance, I don't know what that might be, but then we'd have different values of this third variable. And so we'd have to make sure that we use the right one of these curves when we're moving from the value of the Reynolds number to get the Euler number. Perhaps you don't need this. I don't think you do in this test. So that's it. Have a look through the notes. Have a look at what we talked about in class. And hopefully this will fill in any gaps in answering the questions which are on the test. Good luck.